about priors and how they represent knowledge that we have. Let's say we are at the end of the 90th century and we perform this analysis. We have 4 supernovae in 10 centuries and we get a posterior probability distribution for a naked eye supernovae, a probability that is this. Again, if we look at this, we do not know the probability to find a supernova. What we get is a probability for a probability. We get a probability distribution on probabilities. We can say the expectation value is here and there is 50% and within 95% confidence we are sure it is somewhere between these limits. We don't get a single number, but we get an uncertainty. We get an error bar to our estimate. Now let's say at the 19th century we get this result. Now let's say we are now in the mid of the 20th century and we would like to at the end of the 20th century we now observed and supernovae, and we take our previous estimation as prior. Recall that we took a uniform probability as prior here, but we are now a couple of years later and now our prior knowledge is more refined. Our prior knowledge is now this and not a uniform distribution. So we can do the same analysis. What is the probability to observe the supernova 1987? So 5 supernovae in 10 centuries with this binomial distribution, with this prior from the previous centuries. And the integral of this used as a normalizing factor gives us this result. The posterior probability distribution now is somewhat different from what we got 50 years earlier because we have updated data and used more refined prior knowledge. So in this figure I show you that our improved prior makes a difference, because if we had used a uniform prior, this would have been the result. This is the red curve, which is centered at 0.5, as we would expect when we started with uniform prior probability. But now we started with a prior probability that is centered at 0.4. So we are favoring probabilities that are centered around 0.4, and now we observe a fifth one. And there is still the probability that we are much closer to 0.4 than 0.5 and still get a fifth supernova. So this probability distribution, given here by the black line, is shifted towards lower values of a supernova rate. So the choice of the prior makes a difference, and this is also a common criticism of the Bayesian approach, that the choice of priors at the end is subjective. When we would have started our analysis for the supernova not with a uniform but with some peaked prior, as we saw now, then the posterior that we get from a peaked prior is much more peaked in contrast to the uniform prior. So the choice of priors matter. However, if we think of an experiment where we constantly update data, the detailed choice of the very initial prior is washed out after a number of steps when the data is updated, and we compute posterior probabilities that are used as priors for the next step and so on. So going further along the experiment, the initial prior loses more and more impact on the final result. We used uniform priors in this example, but there might be cases where a uniform prior is not a good choice. For example, in cases where we have, for example, yes or no results for an experiment and very little chance to get values in between, then we can use, for example, these two different priors from Jeffreys or from Haldane that look like this. So we have functions that are peaked very much at very low and very high probabilities, reflecting yes or no experiments.